All right. So yeah, 8:35, and welcome back from your break. Hopefully, you guys got a chance to relax. Think about probability. So we're here on October 30th. So we're one class behind. But I imagine we'll be able to catch up pretty quickly. So today we're not actually talking about the birthday paradox, although we might get to it. We might start on it. We'll be talking about uniform probability. Other than that, your assignment 2 was supposed to be done marking today. I don't think that's going to happen. Looking at how many are still outstanding, unless the TAs have a little burst. So I'm guessing sometime later this week, your assignment 2 will be done. But yeah, questions before we get started? Okay. So today we're going to talk about uniform probability, which is a lot like regular probability. It's just more uniform. So just as a reminder of what probability is and the things that we use to compute it. So we have a sample space S, which is just a set. It's a set of possible outcomes, right? So we perform an experiment and there's a bunch of things that can happen. I flip a coin, for instance, it could come up heads or it could come up tails. We sort of ignore the idea that, it could land on its edge or a seagull could come grab it, stuff like that. The stuff that's out of the usual realm. So these are well-controlled experiments. And then we have a probability function that maps each element. Let me just of our sample space to some real number such that that real number is between 0 and 1, right? So the probability of any event has to be somewhere between 0 and 1. And if I sum up all of the probabilities of all the events, they have to sum up to 1, right? So that's sort of the foundation of probability, is that we have a sample space, a bunch of events, they have come up with a certain probability, and those probabilities sum to 1. Sorry, I said events, I should have said outcomes, because an event is a subset of S. So an event is one or more outcomes, or maybe even 0 outcomes. So yeah, so if I have, some sample space and S, and I have an event A that is a subset of S, then the probability of this event A happening is the sum of all of the probabilities in A. Right, so each of these, it's a W, it's supposed to be omega, but so each outcome in my event has a probability. I just add them up. That's the probability of my event happening. Right, so there's a nice little Venn diagram. The probability of S, well, S is a subset of itself, so it is an event. So the probability of S is 1. The probability of the empty set, probability of nothing happening is 0. Okay, so something always happens. In fact, every time we run our experiment, exactly 1 outcome occurs. And then we have things like the complement rule that we can apply to probability, right? So this is similar to the complement rule of sets with good reason. So the probability of A, if we can't compute that directly, we can try and compute the probability of A complement. And then the probability of A is 1 minus the probability of A complement. Right. And if we want, say, the intersection, or sorry, if we want the union of 2 sets and we want to determine the probability, and these 2 events, A and B, are disjoint, meaning they don't have any outcomes in common, that means I can use the sum rule of probability. So the probability of A union B is equal to the probability of A plus the probability of B, right? And this is the sort of Venn diagram representing that. A and B are completely separate. If, however, A and B overlap, then I have to use the inclusion-exclusion rule of probabilities. So if I want to determine the probability of A union B, it's the probability of A plus the probability of B minus the probability of A intersect B, right? Because when I added all of these probabilities, and then I added all of these probabilities, I counted everything in here twice. So then I have to subtract it once to get the actual probability. And that's basically as far as we got, right? So today we're going to keep talking about that. Or any questions before we continue? Okay. So today we're going to keep talking about that, but we're going to talk about a special probability function or a special probability space. And that is a space where we have uniform probability, right? And this is a lot of what we end up working with in probability day to day. So that means every possible outcome in S has the same probability. And, since we know all of the probabilities must sum to 1, then we know that the probability of any individual outcome in S must be 1 over the size of S. Okay. Sorry. Okay. And which is, we've actually worked with uniform probability last lecture. This time we're just defining it explicitly. But what this means exactly is that now when we want to find the probability of an event, it all comes down to counting, right? We simply count the size of our sample space and we count the size of our event. So if I have an event A, then the probability of A is the sum of all of the individual probabilities of every outcome in A. And of course, every single outcome has probability 1 over the size of the sample space. And the number of these outcomes, well, that's the number of outcomes in A, right? So then my probability of A is simply the size of A over the size of the sample space. Right, so I roll a die, my sample space, it's uniform probability, my sample space has a size of 6. The probability that I roll a 1 or a 2 is 2 over 6. Right? So other examples, rolling a die, flipping a coin, drawing a card, a lot of gambling. So we use a lot of gambling examples because gambling is, in some sense, one of the purest forms of uniform probability. Or at least the things that they do in gambling. This is not a suggestion on a lifestyle choice. Hopefully this class will convince you that the house always wins and gambling's a bad idea, if nothing else. But they do make good examples for this class. Okay, so let's take Lotto 649. So the rules of Lotto 649, they have a bunch of, numbers that they draw at random. I'm not sure how they do it now. They used to have a big tumbler with a bunch of little ping pong balls in them with numbers on them. And what they do is they draw a 6-element subset from the set of numbers 1 through 49. So that's why that's the 649. So now we want to, of course, if we're playing the lottery, we're going to choose 6 numbers for ourselves. And then if these 6 numbers are the same 6 numbers that are randomly drawn, then we win millions of dollars. All right, so let's say we chose 1, 2, 3, 4, 5, 6. And we're wondering if this is a good bet or not. It doesn't feel very good, right? It seems like it probably won't win. But the fact is, no matter what numbers we draw, we probably won't win. But yeah, so is this a better idea or something like this may be a better idea? Something that looks sort of more like the numbers, less regular. Right? These actually won in 2014. So yeah. So when they spin the tumbler, they take the balls out. Each of those balls is drawn with the as completely random as they can make it. So we say that this has a uniform probability space or a uniform sample space. So every set of numbers comes up with, by definition, with the same probability. But yeah, what is that probability? I think oh, there we go. So yeah, our sample space S, all subsets of size 6 chosen from the numbers 1 through 49. Okay, so how big is S? Right, so this is just counting. So we define our set S as all possible choices of 6 numbers from here. And how many are there? Yep. Yeah, precisely. So I think I get to that eventually. So yeah, we're going to use the binomial coefficient. First, we'll talk a little bit about what exactly this procedure is. Right. So when I drew these numbers, they didn't necessarily come out in that order. I don't really care about the order that they were drawn in. All I care is that these particular numbers came up. You'll notice that we put them in sorted order, right? Just to be sort of organized. They could have come out in any order. I don't care about the order. I just care about the numbers that I chose are the same as these numbers. So when we do that, order doesn't matter, which means yes, we're going to use a binomial coefficient, right? So we're going to say, out of this bin of 49 numbers, I'm going to choose 6 of them. And yeah, that will have size. 49 choose 6, right? And 49 choose 6 because the order of these numbers doesn't matter. It's just a set. Okay. All right. Questions?
Well, for 13 million, that is one of the 13 million.
Is it?
Yeah. Looking at the technical system following.
Okay. So yeah, that means if I take the event that these were the numbers that were drawn, well, that has probability 1 over 49 choose 6. And if I take the event, you know, and it has, yeah, 1 over, what is it, 1 over 13 million? Okay, so, or approximately this. And the probability of these numbers being drawn, this is also 1 over 13 million. Right, so whatever numbers we choose, we have the same probability. Now this looks funny, but technically speaking, you're as unlikely to win the lottery using those numbers as any other numbers. Yeah. Okay, so that's a simple introduction. Again, we're gonna talk about some cards. So a deck of 52 cards. We have 4 different suits. So we have spades, clubs, hearts, diamonds, and we have 13 different ranks. Right, so we have we start with an ace, which sort of is a 1, or sometimes the high card. Then we have 2, 3, 4, 5, 6, 7, 8, 9, 10, and then Jack, Queen, King. So 13 ranks, 4 suits. Every rank has, you know, so if I look at all of the 10s in my deck, there is exactly 4 of them. If I could draw. So 10 of spades, 10 of clubs, 10 of hearts, and 10 of diamonds. And that's true for every rank. So every rank has 4 different suits. And so I have 4 times 13 or 52 cards. So then in poker, we're going to be dealt 5 cards. Okay? And then we want to try and build a strong hand. So there's rules of poker, and it's largely based on probability. But certain hands will beat other hands, and then you win money from whoever you're playing with. So when we, with just straight up poker, we get a hand of 5 cards drawn uniformly at random from whatever remains in the deck. And as far as we're concerned, if we don't see any other cards, it doesn't matter how many other people are playing, you can still, your probability of getting a certain hand of 5 cards is the same, right? No matter if I've already dealt out 5 cards here or 5 cards there, because those were drawn at random as well. Okay, so my sample space is all of the ways I can draw 5 cards from a deck of 52 cards. And then whether or not my hand of cards beats somebody else does not depend on the order that I drew them in, right? Just depends on the set. So then the size of my sample space is going to be the same as Lotto 649 or similar. I have a set of 52 cards. I'm drawing 5 of them, right? Order doesn't matter. I'm just going to rearrange them in my hand anyway. So the size of our sample space is 52 choose 5. And then we want to compute the probability that we have a good hand, right? So one of the good hands in poker is a full house. A full house is 3 of some rank, 3 cards of one rank, and 2 cards of a different rank. So I have 5 cards altogether. These are both examples of a full house. In this case, I have 2 aces and 3 queens. And over here, I have 3 kings and 2 twos. Right, so those are both a full house, and it's a pretty good hand. You have a pretty good chance of winning if you get a full house. So we want to compute the probability that I get dealt my first 5 cards and I get a full house right away. All right, so it's a shuffled deck. My hand is drawn uniformly at random. So of course my sample space is 52, choose 5. My event is, well, okay, so here's one example of a full house. I can draw the 7 of hearts, 7 of diamonds, 3 of spades, 3 of clubs, 3 of diamonds. So 2 7s, 3 3s. Yeah, so my event A is that out of my, when I get my 5 cards, I have 2 of one rank and 3 of another, or in other words, a full house. And my probability of this event using uniform probability is the size of the set A over the size of the sample space. So I get dealt 5 cards. I want to count all of the possible, all of the possible hands that are a full house out of those, out of all possible hands of 5 cards. So how do I do that? Again, we're right back to counting, right? So we're going to use the product rule. And to use the product rule, we use a procedure. So we're going to define a sequence of tasks that in some sense builds our hand of cards. So task 1, and we can do these in any order, right? It's product rule, so whether I choose the cards of rank 3 first, or sorry, the 3 cards of the same rank first, or the 2 cards is immaterial, right? Product rule, multiplication is, what is it, commutative? I forget, I think that's it. Okay, so task 1, we want 3 cards of the same rank. There are 13 ranks to choose from, so I'm going to choose one of them. There are 13 ways to do that, right? 13, choose 1, or just 13. Once I have chosen a rank for those 3 cards, I need to choose which of the 3 out of my 4 cards to choose, right? As mentioned, if I have an ace, there are 4 different aces. Yeah. And diamonds, yeah. So I have to choose 3 of them. So 4 choose 3, right? Binomial coefficients, again, I don't care which order. I just care which of these 3 I choose. 4 choose 3 ways to do that is also equal to 4, right? Because choosing 3 is the same as choosing the one that I leave behind. So there's 4 ways to do that. Okay, so I've got my 3 cards. I've chosen the rank. Sorry, I've chosen the rank of my 3 cards, and I've chosen which of those 3 cards to put in my hand. Now I'm going to find the 2 cards of the same rank. I can't choose the same rank as I chose before, which means for this task, I will have 12 ways to choose it, right? So whatever I chose, let's say I chose 7 for my 3 of a kind. That means for my 2 of a kind, I have to choose from everything but 7, which is 12 ways to do that. Once I do that, again, if I choose, let's say 4, well, there's 4 different 4s, and I want to choose 2 of the available ones. So I have 4 cards of that rank, and I choose 2 of them. There's 4, choose 2 ways to do that. In some sense, you know, we said 12 here, and we said 13 before. Again, you could write these all as binomial coefficients, right? 12, choose 1, 4, choose 2. So using the product rule, These are my sequence of tasks, and these are the number of ways that I have to do each of these tasks. So I simply multiply them together to count my event A. Okay. And again, technically, these are all binomial coefficients. But we can write 13 choose 1 as 13 and 12 choose 1 as 12. My sample space, 52 choose 5. Then my probability of A is simply this. So the probability that I get a full house is small, tiny, but 0.1%, slightly over that. But yeah, questions? Okay. Yeah, we won't do this one. We'll go through this one really quick and then we'll move on to something else. I just want to show you something because I often get this question. So let's say we're going to choose, it's the same game, poker, we get 5 cards. We want the probability that we get a flush. And what a flush is that all cards have the same suit, right? So that means whatever the numbers we'll say we're going to even count the ones that are in order, which is technically a different outcome. But so I have 5 cards and they're all hearts, for example. Again, the sample space is the same, right? So all of the ways that I can choose 5 cards from my deck of 52 is 52 choose 5. I'm going to develop a procedure. Again, I'm using the product rule to count the number of ways I get a flush. Well, what's the first task I could do? Or it doesn't matter which order we do the tasks in, but what's one task I need to do? Right, so I need 5 cards. They're all going to be different ranks, but they're all going to be the same suit. Yep. Yeah, I can choose a suit. So I'm not sure if I did that first here, but yeah, I can choose a suit. There are 4 suits to choose from. Try that again. There are 4 suits to choose from, so I have 4 choose 1 ways to choose a suit. And then among those, in that suit, there's 13 different ranks, and I need 5 cards for my hand. So how many ways are there to do that? Yeah. Yeah. So 13 choose 5, choose 5 ranks out of 13. Okay, and then yeah, so my the size or the number of ways that I can get a flush out of all my possible hands of 5 cards is 4 times 13 choose 5. So then my probability that I get a flush is 4 times 13 choose 5 over 52 choose 5, which is 33 over 16,660. 16,660, yes. Okay, so that's all very straightforward. Questions about that? Okay, so now I'm talking about cards, but you can relate this to anything, right? So I chose things, I said the order doesn't matter, so I use binomial coefficients. But what if you said, well, what if I count the ways I can be dealt the cards in the certain order? So now when I get my 5 cards, I want to count all the different order that they can come in. Right, so I'm going to have a card number 1. That's the first one I'm dealt. Card number 2. That's the second one I'm dealt. Card number 3, et cetera, et cetera. So now the size of my sample space, well, spoiler alert. My first card, I have 52 choices. My second card, I have 51 choices. My third card, 50, 49, 48. Right, so whereas before we had 52 choose 5, where order didn't matter. Now we have 52 factorial over 47 factorial. Okay, so we have a slightly different number. In fact, these are different by an order of 1 over 5 factorial, right? If I write out 52 choose 5 is 52 factorial over 5 factorial times 47 factorial. So they're very close, off by an order of 5 factorial. Okay, but I should get the same probability, right? So let's count the ways I can get my flush now. So again, I'm going to have a sequence of tasks, but now I'm going to take into consideration the order that I receive these cards. The first thing I do, I'm going to choose a suit. There's 4 ways to do that. That's no problem. But then I'm going to look at the cards I get in order. So I'm going to have a card number 1 that I get dealt. I have 13 choices for that. Out of the 13 available in that suit. My second card, I have 12 choices for that. My third card, I have 11 choices. So the size or the number of hands that are a flush, taking order into consideration, is 4 times 13 factorial over 8 factorial. So then my probability that I get flush is the size of my event that I get a flush over the size of the sample space. These are the numbers that I computed for both of those. When you work it out, you get 33 over 16,660, yeah. So yeah, that's, if we go back. So it is, if I multiply all of these out, is 4 times 13 times 12 times 11 times 10 times 9. And if we just look at this part, then this is sort of a factorial, right? So this is sort of factorial. Let me see here. If I wrote this out completely, right? If I wrote out 13 factorial completely and then divided it by 8 factorial, okay, so on the top, I have 13 factorial. On the bottom, I have 8 factorial. And if I expand those out and then I look, then these parts cancel and I'm left with 13 times 12 times 11 times 10 times 9. So yeah, this is simply a way to express this number here. Other questions? Yes, it's what is it? So these are injective functions. Yeah, there is a formula for it. Technically, this is the number of injective functions from A to B, where B has size 13 and A has size what is it, 5. Yeah. So yeah, there is a yeah, exactly. Precisely, yeah. So it's, 13 is our n, and then if you used n minus k, our k would be 5. So n factorial over n minus k factorial. Yes, that is correct. Good. Other questions? Okay, so we get the same answer, as you should, right? So when you talk about if you ask me, oh, should I do this? Should I count the order? Should I not count the order? Just be consistent, right? So your sample, whatever you do for your sample space, you should do that for your event as well. Or choose one. Oh, sorry, I missed, whenever that happened, I missed it. All right, questions? Yeah, so the permutations cancel out if I decide to do things in order. There's some other examples here you can look at. I'm going to skip those and move on to Newton. This is an ancient problem. Newton, I'm going to call him Pepys. I don't know how to pronounce his name. I should Google that at some point, but so in 1693, before all of this mathematics was developed, Pepys asked Newton to solve this problem. And the problem is, as follows. I do an experiment, or I do 3 different experiments, and I want to know the probability, which has the most probability of happening. So one experiment is I roll a single 6-sided die 6 times, and then I have A is the event that at least one of them is a 6. Right? So if I roll a die 6 times, what's the probability that at least one of them is a 6? And then I'm going to do a second experiment. I'm going to take that same die, I'm going to roll it 12 times, and I'm going to, the question posed to Newton was, specifically the question posed to Newton was, what is the probability of this? But the question was, which has the greater probability? I get at least 1 6, I get at least 2 6s on 12 die rolls, or I get at least 3 6s on 18 die rolls. Okay, so that's the problem that he posed, and Newton guessed correctly. Pepys was wrong, but they both didn't do it correctly. So Newton got to the right answer by accident. But yeah, so we, now that we have all of this knowledge about how to compute probabilities, we can compute and see which of these is correct. So Pepys thought that 3 was most likely, right? So if I roll a die 18 times, I get at least 3 6s, and that 2 was the second most likely, and that 1 was the least likely. So spoiler alert, he was wrong. Newton was right. Newton guessed the other way, that number 1 was the most likely, and number 2 was the second most, and number 3 was the least likely. So we're going to prove that. All right, everybody clear on what the question is, what we're trying to prove? Okay. All right, and back in, when they did this, they didn't have all of these structures that we're going to be using. So this is sort of easy for us to compute, but it was difficult back then. So we're going to start by doing experiment number 1 and computing the probability that A happens, where we get at least 1 6 in 6 rolls. So what is our sample space? Okay, so we're doing our experiment. We're rolling 1 die 6 times, or 6 dice, however you want to phrase it. So our sample space is all of the outcomes of rolling 6 dice. And the size of our sample space, well, we're going to write it like this. Right, so R1 is roll 1, R2 is roll 2, all the way up to roll number 6, and each of them has 6 possible values. So what is the size of our sample space in this case? Okay, so you can think of it as a string, right? It's a string of 6 characters, and each character is taken from the numbers 1 through 6. So if I wrote this down, I could write 5, 4, 3, 1, 2, 6. Right, so that's one possible string, and that's one possible outcome. I could write 6, 6, 6, 6, 6, 5, 1, 1, 1, 1, 1, 2. There's a whole bunch of outcomes. But really, it's the same as counting strings. Right? So we did this before with passwords, right? Except instead of having 6 numbers to choose from, we chose from the letters of the alphabet. So we can count this exactly the same way. We can look at our 6 dice and say, well, I have 6 possible outcomes here. I have 6 possible outcomes here, 6 here, 6 here, 6 here, 6 there. And then I use the product rule, and I get 6 to the power 6 ways. So the 6 to the power 6 is the total number of outcomes from rolling my 6 dice. Does that make sense? Okay. Yes. Sequence of tasks, roll 1, die 1. If we did it more formally using the product rule, you can break it down into a sequence of tasks, but they're exactly the same as what I just showed you, right? I'm choosing which value is on my first die, which value is on my second die, etc. And I get 6 to the power 6. Okay. So now we want to count the size of A, right? So it's a uniform probability space. These are fair dice. which means each outcome has equal probability. So this is a simple counting problem now. So my event A is that I rolled at least 1 6. So how am I going to count this? Well, at least one is, I mean, that's not precise. I could express it more precisely. So yeah, this is our probability. This is what we want to compute. So we need the size of A. I can break A down into subsets. So A1 is the event that exactly 1 6 was rolled out of my 6 dice. A2 is the event that exactly 2 6s were rolled out of the 6 dice. A3 is exactly 3, etc. I could have all the way up to 6. Okay, and this will work. I could do this. It's a lot though. I have to compute all of these individually, and they're not that hard, but it's more work than I want to do right now. Right? So what do we do when counting a problem size directly is difficult? Yeah, we're going to count the complement of A. So event A naught or A complement is that we didn't roll any 6s, right? So if I roll at least 1 6, then these are all of the dice rolls that have at least 1 6. And then the complement of that is, of course, 0 6s, which is actually kind of easy to count. So if I want to count, I could rewrite that as on each of my 6 dice, I rolled some number from 1 to 5. And then I can break that down and do a sequence of tasks, or I can make it into, a sequence of 6 characters, and then each character is taken from the numbers 1 through 5. Both of those are equivalent. But yeah, task 1, task 2, up to task 6. And I have 5 ways to roll a 1 through 5 on die 1, 5 ways to roll a 1 through 5 on die 2, etc. So then I have 5 times 5, 5 to the power 6 ways to roll no 6s on any of my 6 die. Okay. So then using my complement rule, well, I'm going to do it 2 different ways. So this is, because we're using uniform probability, and uniform probability is just counting sets, I can use the complement rule of sets, right? Which is what this is. So if I wanted to count A and I couldn't count it directly, I could instead count my sample space and a complement. Right? So a complement is 5 to the power 6. My sample space is 6 to the power 6. So my probability of A is the size of A over the size of S, which is 6 to the power 6 minus 5 to the power 6 by the complement rule over 6 to the power 6. And I can rewrite that as 1 minus 5 to the power 6 over 6 to the power 6. So I use the complement rule of sets. But of course, we have an equivalent complement rule of probability. But questions on this? Okay. So the complement rule of probability is that the probability of A is equal to 1 minus the probability of A complement. Well, the probability of A complement is the size of A complement over the size of S. And well, I already know those 2 values. It's 5 to the power 6 over 6 to the power 6. So we get the exact same answer. Right. So probability we're using in uniform probability spaces, you can come to the same answer in a lot of different ways, right? And it's kind of nice because we're just reusing counting, and a lot of this stuff is going to be kind of intuitive. There's going to be problems that are not intuitive, especially when we get to conditional probability, then it's going to look a little different. But for these, you can almost sort of trust your intuitions. All right, questions? Okay, so we've done experiment number 1. Let's do experiment number 2. we're going to roll a 6-sided die 12 times, and then we're going to determine the probability that we get at least 2 6s out of those 12 rolls. Okay. Yes, so this is experiment 2. The size of our sample space, same calculation as before. I have 12 dice now. All right, so each of those 12 dice, I have 6 choices. And I have 12 positions, so 6 times 6 times 6 times itself 12 times, 6 to the power of 12. Right, so this is a different sample space from experiment number 1. We named it the same thing, which maybe, hopefully is not too confusing, but it has a different size. And then the probability of B, well, let's cut to the chase, right? So I roll at least 2 6s on 12 dice. Of course, I can count the number of ways I roll exactly 2 6s on 12 dice, plus the number of ways I roll exactly 3 6s on 12 dice, et cetera, up till 12 6s on 12 dice. I can do that. It seems like a lot of work. So we're just going to cut to the chase and go right to the complement rule. So the complement of rolling at least 2 6s on 12 dice, well, I can break that into 2 separate events. So event B1, I will say I roll exactly 0 6s on my 12 dice. And event B2, I'll say I roll exactly 1 6 on my 12 dice. So again, it's case analysis, same as we would have had to do if we computed B directly. There's just less cases. And so I'm going to have to add these up. These are disjoint, but yeah, we can compute these more easily. So now we have B complement. The size of B complement is equal to the size of B1 plus the size of B2. Now we have to count the size of these 2 events. Okay, so B1, well, that's simple, right? It's pretty much the same thing we did for the first experiment. We're rolling 12 dice in this case, but each of them can only take on the values 1 through 5. So I have 12 locations, 5 choices in each of those locations. So it's 5 to the power 12. Or I can use the product rule, or I can map it to, the number of passwords or the number of strings where I use characters 1 through 5. Okay, so B1, 5 to the power 12, same as similar to our first experiment. B2, this one's a little trickier. So I have exactly 1 6. 12 dice, they're numbered 1 through 12. Right, so I'm rolling a single die 12 times. We're going to impose this order on them because it's easier to count that way. So if I have exactly 1 6, the first thing I have to do is, well, it could be that 6 occurred on the first roll. It could be that 6 occurred on the second roll, on the third roll, fourth roll, up to the 12th roll. So the first thing I'm going to do is choose one of my 12 dice for this 6 to come up on. Right. And then task number 2. So yeah, I choose one of the 12 dice. So I have, well, let's just draw a few of them. So I say a 6 comes up here. That was my first task. And then I look at all the rest of my dice. So I'm going to call this die number 2, even though this is die number 1. Yeah, this is probably not a good way to write it. But I'm going to look at the next available die, and I'm going to choose a number for that. So 1 through 5. And again, it really doesn't matter which order I do these in. So I'm going to choose somewhere 1 through 5 on here, 1 through 5 on here, and 1 through 5 on here. So my first thing I do, I have 12 dice. I choose one of them to be a 6. So there's 12 ways to do that. And then each of the remaining 11 dice, I choose a number 1 through 5 for those dice, and there's 5 ways to do that. Right, so my size of B2 using the product rule is 12 times 5 times 5 times 5, 11 times. So 12 times 5 to the 11. Right. Questions? Okay. Then I can simply add them up. Right? Because they're disjoint. How do I know they're disjoint? Well, each outcome is a roll of 12 dice. On the one set, one of those dice is a 6. In the other set, none of them are a 6. So there cannot possibly be two outcomes that these two sets have in common. So I can use the sum rule here to compute the size of B complement. Oops. So yeah. B complement is B1, size of B1 plus B2. Size of B2, it's 5 to the power 12 plus 12 times 5 to the power 11. And now I can compute the probability of B as 1 minus the probability of B complement, which is the size of B complement over the size of the sample space. And the size of B complement is 5 to the power 12 plus 12 times 5 to the 11 over 6 to the power 12. And if I put that into a calculator, I get 0.6187. Okay. So I've done 2 of my experiments. Here I've differentiated between the 2 different sample spaces. I computed the probability of A as 1 minus the probability of A complement, and the probability of B, I did the same thing. And wow, my computer's really slowing down. But yeah, so the probability of A is greater than the probability of B. So I'm more likely to roll 1 6 on 6 dice than I am to roll 2 6s on 12 dice. So yeah, questions so far? All right, we're going to do C. C is very similar, slightly more difficult. Well, there's just more cases. So yeah, I'm going to roll a die 18 times. C is that at least 3 of those are 6s. My sample space is, the same thing as before, except now I have 18 dice, 6 choices for each of them. So it is 6 to the power 18. And then event C, again, we're going to use the complement rule. I mean, we can go through the same thing we did before and look at how many cases on the one hand and how many cases on the other. This has 3 cases now, but it's still a lot less than 15 cases on the other side. So complement rule it is. So if I count C complement, I can have exactly 0 6s, and we'll call that event C1. I can have exactly 1 6, we'd call that event C2. And then we can have exactly 2 6s, and we'll call that event C3. So this is all the ways I can have less than 3 6s. Okay, so now we're just going to count them individually using all of the same steps that we did for the other 2. And again, we're going to use the sum rule to count C complement because all of the outcomes in this set are disjoint from all of the outcomes in this set and all of the outcomes in this set, right? If I have exactly 0 6s, then that means I do not have any rolls with 2 6s, for example. So count C1, well, that's simple. 0 6s on 18 dice. I choose the numbers 1 through 5 for all 18 dice. So the product rule tells us this is 5 to the power 18. All right, C2, this is the same thing I did with B2 before. I'm going to start, I get exactly 1 6. So I'm going to choose one of the 18 dice to show that 6. There's 18 ways to do that. And then the remaining 17 dice, I'm going to choose a number from 1 through 5 for each of those 17 dice. Right, so then if I use the product rule, I get 18 times 5 times itself 17 times. So 18 times 5 to the power 17. Okay, so C1, C2, no surprises there, very similar to B1 and B2. C3, exactly 2 6s. Well, I'm going to use basically the same procedure. Except now I have to choose 2 dice to show a 6 out of 18. So how many ways are there to do that? I have 18 dice or a single die rolled 18 times. So I need to choose, yeah, 18, choose 2, right? Because it doesn't matter which order, they're both going to get a 6, right? So whether I choose, if I had a 6 here and a 6 here, it wouldn't matter if I chose 1 and 3 or 3 and 1. So because order doesn't matter, binomial coefficient, 18 choose 6, sorry, 2 choose 2. And then I'm going to go, I have 16 dice that don't have a value. They can all have a value from 1 through 5. So I'm going to choose the value for each of those 16 dice. So yeah, I have 18 choose 2 times 5 times 5 times itself 16 times. So 18 choose 2 times 5 to the 16. And then, well, that is the size of C complement. If I add them all together, these 3 disjoint sets, and I can compute the probability of C now using the complement rule of probabilities. So 1 minus the size of C complement over the size of S. So I get this nice big number that I can plug into my calculator or Wolfram alpha. I get 0.5973. It's okay. It's okay. It seems appropriate, yeah. No, it's okay. It's fine. That's how you woke everybody up. It's great. Everybody. All right. So yeah, we have probability 0.5973. Questions on how we got there? Okay. Yeah. So if I list out all of the outcomes now, my probability of A, these are 3 different experiments, but the probability of A in experiment 1 is 0.6651. Probability of B is 0.6187. The probability of C is 0.5973. Yeah. So yeah, it turns out Newton was right, but if I remember correctly, then he did it the wrong way. But yeah. Questions? Somebody asked me what would happen if you kept going, which I thought was an extraordinarily good question, right? So what if I rolled now 24 dice and I wanted to get 4 6s, or 30 dice, I wanted to get 5 6s. What happens to these probabilities? I don't know. I would have to think about it. I think we started working it out in class, but I think it might converge on some number. Yeah, but I don't know. Interesting problem to think about anyway. Okay, so that's it. This is a uniform probability space because we used fair dice. We rolled 6, 12, 18, it didn't matter. Each outcome had equal probability, and that means determining the probability of any given event comes down to simply counting the sample space and the size of the event. Okay. And yeah, I think that's, oh yeah. So I did make some extra slides that sort of take this problem a little bit further, but the procedure is exactly the same. So I'm not going to show you that. We're going to jump into, I think, the birthday paradox. Yeah, I mean, this you can look at, but there's nothing different about the procedure. Right, birthday paradox. So birthday paradox, is not actually a paradox. It's just a surprising result in probability, and there's a bunch of those, right? So anybody know what the birthday paradox is? Yeah, a couple of people. Yep, 23 people actually. So, and it goes up really fast, right? So what is the probability of two people? If I have two people, what's the probability they're born on the same day? This, I don't know, anybody want to throw that one out there? You can use your intuition here, right? So assuming that everybody is, assuming we have a uniform probability space. So there's 365 days in a year. We'll ignore leap years. So the probability of being born on any given day is 1 over 365. And then I have two people. What is the probability that they were born on the same day? I mean, we can compute it. Just wondering if anybody has some instincts. Because it really is sort of old school probability, right? Stuff you might have learned in high school. If there's two people, it's 1 over 365, right? So I just, person A is born on whatever day, and then person B is born on some random day, and then the probability that they match is 1 over 365. We're going to compute that. So that's unlikely. But what happens is the more people you get together, the more likely it is that two people have the same birthday, right? So what's, you guys don't have to share your birthday if you don't feel comfortable, but maybe we can run the experiment here. I've never had this experiment fail. It came close, but yeah. So I was born on January 23rd. Anybody born? September. Yeah, September. Which day? September 23rd. Right. Anybody born on September 23rd? All right. You can. Anybody want to share? Yeah. March 28th. You were born on March 28th? Oh. All right. When were you born? July 5th? Nobody? Yeah. April 4th? Yeah. May 22nd? Oh, we might fail today. I don't know. Yeah. February 6th. May 10th. Sorry, what was it? June 29th? February 5th? Oh. Anybody else? We didn't get to yet? October 16th? It could have, I mean, we don't have, so the break even, the 50-50 shot is 23 people, which we're going to compute, but anybody else? October 22nd? April 28th? August 10th? Anybody else? Oh, no, it's first time. First time we don't get anybody. Yeah. March 15th? 18th? Oh, it doesn't look like we're going to get it. Anybody else? Nobody's going to remember anybody's birthday. It doesn't matter. But yeah. April 27th. Oh, I mean, it's, if you guys aren't matching up, then it's nobody. Was that somebody's in the chat? Oh, did somebody match? You're going crazy. June 29th. Somebody said that? Yeah, so we got two. All right. So yeah, we didn't have that many people, but we still had a match. Oh, that's cool. Hasn't failed yet. All right. So yeah, that is the birthday paradox. Two people, it's really unlikely that they have the same birthday, but you get 23 people together and suddenly it's pretty likely. And in fact, it gets close to 100 fairly quickly. So yeah, we're going to talk about the birthday paradox, and we're going to compute the probability. We're going to do it on the next set of slides, however. Okay. All right, so officially the birthday paradox, we're going to compute it in a sort of a general sense. In fact, I think, yeah, I think I have to update these slides. I think I did something really annoying on them, where I jump back and forth between the two problems. But so when we consider birthdays, we have 365 days or, 366. Somebody could have been born on a leap year. But we can generalize this problem to any number of days. So let D be the number of days in a year. And yeah, it doesn't matter which number we take. And in fact, there's a lot of, like every other problem we show you guys, this generalizes to lots of similar problems. So birthday paradox is not just for birthdays, it's for a bunch of things. And then we're going to have some number of people, at least 2, and everybody has a birthday on precisely one day, and we're going to assume it's a uniform probability space, right? So that means everybody's birthday is chosen from our 365 days or whatever number uniformly at random. And then what is the probability that 2 people were born on the same day? And this is known as the birthday paradox. It's not really a paradox. It's very straightforward, but it's surprising. Okay, so we're going to, of course, use what we know about probability to compute this. So we want to define a sample space and an event. And since it's uniform, we're just going to use counting. So what is the sample space? Well, I'm going to look at all of the people that are in my group. I have n people, and each of them has a birthday. So if I give everyone a number 1 through n, then I'm just simply going to write down everybody's birthday in a string, right? So yeah, so B1 is a number from 1 through D, which is the birthday of person 1. I should go back and fix these slides. B2 is a number 1 through D is the birthday of person 2, and all the way up to Bn. So I have n numbers. Each of them is a value 1 through D. So I can write them as a tuple. I can write them as a string. These are similar to my dice. It's just a collection of values, right? A sequence of values. In this case, I have n values, and each of them has a value 1 through D. All right, so this is, yeah. So we're gonna talk about, we're gonna let D equal 365 and n equal 3, and yeah. So let's start with a concrete example. I really don't like the way I made these slides. We should go to the general case later and stick to the specific early, but maybe I will adjust them for next class. Anyway, so I have 3 people. Each of them has a birthday chosen uniformly at random from 365 days. So what is my sample space? It's a collection of 3 values. Right. B1, B2, B3. And what is the size of my sample space? Right. So again, this is just the product rule. It's the same as I could think of it as a string of 3 characters, and each of them comes from an alphabet of size 365. Right. So I have 365 choices for B1, 365 choices for B2, and 365 choices for B3. And yeah, so if I listed them all out, I would have 111, 112, all the way up to 365, 365, 365. But to count them, of course, I just use the product rule. And I get 365 cubed. Okay. So yeah, simple product rule, 365 choices for each of them gives me 365 cubed. And if I list them all out, they are all some sequence of three numbers. Okay, so that's our sample space. This is what our outcomes look like. So when I perform my experiment now, I have my three people. They each have a birthday on some day, and that corresponds to one of these triples of three numbers, right? So this 55 is, what is it, February 25th, 24th, or something like that. All right. So, yeah. So my outcome then is one of these triples, which corresponds to the birthdays of the three different people. And if I choose, for example, this outcome, 55, 55, 10, that means person one and person two have the same birthday. Right? Same number, same birthday. So my sample space is here. My event is that at least two people have the same birthday, and it corresponds to any triple where I have two matching numbers, or perhaps three matching numbers. That also counts. Okay. So we want to count, if we want the probability out of three people that two people have the same birthday, well, we have the size of our sample space. We want to count all of these outcomes where at least two numbers match. Okay. So we can break this down into two subsets, same as we did with the dice. So we can think about how many outcomes have all three numbers the same. I mean, I'm not showing the list anymore. Let's go back. So here is my sample space S. So how many of these outcomes are there where all three people have the same birthday? Yep. Yep, 365, right? Hopefully everybody can see that. I have 1, 1, 1. I have 2, 2, 2. I have 3, 3, 3, etc. Yeah, so 365 of those. So now I want to count all of the possible outcomes of my sample space where exactly two people have the same birthday. Okay, so exactly two, not at least two. So I need to, again, I'm going to use the product rule. So I'm going to come up with a sequence of tasks to count the number of ways that I can do this. So I need two things. I need a number that two people are going to share, and I need to figure out which two people share that number, right? So maybe they're both born on January 1st, so that's one choice. The other choice is which two out of the three are born on January 1st, right? So I can use the product rule here to count the number of outcomes with exactly two people sharing the same birthday. So I choose two out of the three people. It doesn't matter which order I do it in, and I choose which day that they share. So 3 choose 2, which is actually 3. Oh yeah, sorry, and I forgot one thing. So there's 3 choose 2 ways to do this. There is 365 ways to choose which day, and then 364 ways to choose the birthday of the third person, right? So that it doesn't match the first two. So yeah, my size of A2 is 3 times 365 times 364. Once again, I've broken down my event into two different disjoint events. So my event A is the event that at least two people share the same birthday. Event A3 is that all three share it. A2 is that exactly two share it. So yeah, the size of A is 365 plus 3 times 365 times 364. So the probability of A in this case is this. And if I compute that out, I get 1,093 over 133,225. Okay. Questions? All right, I'm also going to, because I did say that I would, so let's sort of very quickly go over what happens for two people. So let's say I have 365 days and I have two people. Yeah, this should be fine. So my sample space then is all possible tuples of size 2, 1, 2, up to 365, 365. Okay, counting my sample space is 365 squared. Yeah, there was actually. Now I remember I did that on the slides that I skipped earlier, but that's okay. So the size of my sample space for n over 2, or n equals 2, is 365 squared. The size of my event A equals 2 people share the same birthday. Well, there's 2 people, so if 2 people share the same birthday, then that means I have 1, 1, or I have 1, 1, or they're both born on the 2nd day of the year, or they're both born on the 3rd day of the year, etc. So the size of A in this case is 365. So my probability of A, I'm going to hijack this, is the size of A over the size of the sample space for 2 people now. So that is 365 squared. And the size of A is 365, which equals 1 over 365. Okay. All right, questions? So yeah, that's because I did mention that earlier. There was some useful stuff on those other slides, actually, now that I'm thinking of it. Yeah, so here's another question to think about. So yeah, the probability that 2 people share the same birthday is 1 over 365. What if I have 366 people? What's the probability that 2 people share the same birthday? Yeah. Yeah, it's 1, right? How do we know that? Yeah, so it's the pigeonhole principle. So if I have 366 people and 365 days, that means at least one day will have 2 people born on that day. And that's the pigeonhole principle. Okay, so that's a bunch of examples of how we compute the probability of this. So now we want to sort of, we want to compute backwards from, so we know how to compute the probability that 2 people are born on the same day for 2 and for 3 people. Now we're going to compute it in general, and we're going to try and figure out exactly where this probability passes the 50% mark. Right, so right. To do that here too as well. All right, so I really sort of, I prepared the other set of slides. I didn't prepare this one so much, so that's why I'm kind of jumping around a bit here. Okay, well, we got 5 minutes. So we know that yeah, so we know we have a sample space. If we have d days and we have n people, then the size of my sample space is d to the power n, right? It's simply a string of size n, and I have d choices for each element of that string. And this is the same as computing, you know, any password, right? I come back to strings again and again because I find they're very useful for explaining these things. Even when they don't look like strings, they often are. And then my event AN, given D and N, is out of these N people, what is the probability that at least, or sorry, it's the event that at least 2 people have the same birthday, and I want to determine the probability of this event. So what we're going to do is we're going to figure out the probability in general using D and N, and then we're going to work backwards from there to figure out whereabouts it passes the 50% mark, right? So 2 things that we know. This problem on 2 people for 365 days, we have probability of 1 over 365. And if we have 366 people and 365 days, then we have a probability of 1. And then somewhere in between there, we have some number of people where the probability is 1/2, right? So we have, so N minus 1 and N, let's say. So we want to find the values for N minus 1 and N where this probability passes 1/2. So that's going to be the goal. I don't think Pn minus 1 and Pn. And to do that, we're just simply going to compute the birthday paradox in general. But I don't think I'm going to. Yeah. So, and how we're going to approach this is that, well, again, we have this at least, right? At least 2 people share the same birthday, which is difficult to count, especially when we start to get higher than 3, right? If we have 4, 5, 6, 7, then we have a lot of cases. So again, we're going to use the complement rule. So having at least 2 people have the same birthday, if we take the complement of that, it's that nobody has the same birthday, which seems like it might be easier to compute, right? So that is going to be the approach. But yeah, I'm not going to get into that today. I didn't really prepare on these set of slides as much as I did on the previous set. So I'm going to leave that for next class. Next class, we'll finish the birthday paradox and we'll start the next, I believe maybe independent events. I'm not sure. But yeah, that's it for today. Hopefully your assignments will get marked this week. Otherwise, welcome back, and I'll see you guys on Wednesday.